Okay, so here's where we're at. So I gave you that quiz back, and it went okay. Could have gone better. Now, you have to realize, so this test coming up on Thursday, okay? You're going to have a periodic table. You have to know those polyatomic ions, okay? Not all of them, but those 10. If there's one that's not listed on there that you don't know, I will give you that formula, okay? But I'm assuming on those 10 that you know the names and you know the formulas, okay? So if you're not confident about this, you need to focus on that. Make flashcards, do something, okay? I don't care what you have to do, but you've got to figure that out, okay? Now, in terms of the cations, you got to be able to use your periodic table. So if I said, hey, let's talk about, I'm going to ask you, say for example, if I could write, that would help. I said, okay, hey, I want you to write the formula for calcium nitrate, okay? Now, keep in mind on this test, number one, you're not going to have the sheet that says, oh, nitrate is NO3 minus. So you'd have to know that. Oh, nitrate, NO3 minus. So how are you going to figure out the oxidation state of calcium? Go to your periodic table. Which group is calcium in? Group 2. What's the oxidation state going to be?
2.
2. Oh, calcium. 2 plus. You can think of it this way in terms of moving these oxidation states. So you can have CaNO3, 2. Okay, so that's what you have to be able to do without hesitation on that test on Friday. Or if I said, hey, here's something, I'll give you this. Copper nitrate. I'll give you that formula, okay, and then expect you to write the name. So there are only certain ones that require more than one oxidation state. Copper, iron, manganese. Those are going to be the big three, okay? Copper, iron, manganese. Just those are those are the only ones I'm going to pick on. Okay, I'm going to tell you straight up. Just know those are the ones that are going to have more than one possible oxidation state. There's more. There's lead. There's tin. Okay, those are going to be the big three. So when you look at this, you realize, oh, the naming part of it is simple. That's copper nitrate. Now, what's the oxidation state of copper? Is it 3 or is it 1? Izzy? What's the oxidation state of copper? Is it 3 or is it 1?
1, 3.
No, you were good at 1.
Okay, 1.
Okay? So it's copper 1 because look, how many nitrate groups do you have?
1.
1? What's the oxidation state of nitrate? 1. So therefore it's in a 1-to-1 ratio, therefore copper has to be 1 plus. Okay? And again, this is all about preparation. So if I were you all, I would make an index card and says, okay, what are the ones that have more than one possible oxidation state? Oh, copper. Copper can be copper 1. It can be copper 2. Okay? So right away, I know it can't be copper 3 because copper 3 isn't an option. Okay? So maybe put that on one side and go, oh, okay, on the other side, I'm going to put, that can be Cu1 plus, and that can be Cu2 plus. Iron, either Fe2 plus, Fe3 plus. Now, manganese gets weird because it can be so many different things, okay? Manganese 2, 3, 4, 5, 6, 7, okay? So that one's a little bit sketchy. But as far as the ions that you need to know that have more than one oxidation state, iron, copper, manganese, okay? Those are going to be the big three. Now, where we left off yesterday, and that's if you're going to start naming compounds that are, and listen to the terminology, binary molecular compounds, okay? So you can have 2 types of binary compounds. You can have binary ionic compounds, and you can have bionic molecular. Okay? All right? Those are your two options. Ionic. Now, the ionic ones are simple. Something like sodium chloride. Sodium's 1 plus, chlorine's 1 minus. Boom, there you go, easy peasy. You could have magnesium chloride, MgCl, that was a whole train wreck, MgCl2, okay? You could have aluminum fluoride. Now, listen to me very carefully how I ask this question. If it's a binary ionic compound, why is there only one possible combination of those ions? Parker. Let me give you a hint. Use the word sum and zero.
The sum of the oxidation states need to be 0.
Yeah, because they're ionic compounds, okay? You have to start with this idea. What makes it an ionic compound is that you are forming ions. And the only way you can form ions is if you transfer electrons from the metal to the non-metal, okay? That's what makes it ionic. If the atom doesn't lose its electrons, then it just remains as a neutral atom, okay? So just by virtue of that name, an ionic compound, that means that you are transferring electrons from one substance to the other. And that only works when you have a big difference in electronegativity, and that difference has to be more than 1.7, okay? So if you look, and this is where you're going to have like typically atoms on one side of the periodic table, your metals on the left side, your non-metals on that top right-hand corner. You have a big difference in electronegativities. You pull electrons from the non-metal to the metal, and you form ions. So the only possible combination I can have is just what Parker said. Because it's an ionic compound, the electrons lost has to equal the electrons gained, and the sum of the oxidation states have to add up to equal to 0. So this is +1, -1, that adds up to equal to 0. This is +2, I got 2 of these negatives, those add up to equal to 0. Aluminum is 3 plus, fluorine is 1 minus, but I've got 3 of those add up to equal to 0. Okay, so that's the only possible combination I can have because of the fact that they have to add up to 0. Okay? Got that? That's it. The only way it's going to work. Now, when you have molecular compounds, these are covalent bonds. Okay? Meaning that these just share electrons. Because they're sharing electrons, I don't have to worry about the sum of the oxidation states because you're not forming ions. Okay? Because you're not forming ions, there's no oxidation states to add up to. Okay? Because they're just sharing electrons. It's like this kind of hippie California kumbaya thing. It's like, oh, dude, let's just share our electrons. Okay? This is all about peace, love, you know. I don't want to take your electrons, but we need to form a bond. Oh, let's just share them. Okay? So this is like the hippie kind of bond. It's like, let's just hang out and let's just share everything, right? Cool. So this is why, for example, here's the classic example. You can have CO and you can have CO2. Okay? So depending upon how carbon bonds, like I said, if you take AP chemistry, this is like a day-long lecture of something called hybridization of orbitals. Carbon can form 2 types of bonds with oxygen. It can form one bond where it forms CO, and you can share electrons in another arrangement, and you can get CO2. So if you tell me, hey, Mr. Burkamp, I need a bottle of sodium chloride, cool. I know the only way that sodium chloride exists is NaCl, because the oxidation states have to add up to equal to 0. Now, if you say, hey, Mr. Burkamp, I need some carbon oxide, okay? Well, great. I don't know which one you want, because there can be more than one combination because of the fact that you're sharing electrons, and you're not forming ions, so they can exist in different arrangements. So this is why you have to use those prefixes, okay? So mono means one, right? So this is going to be carbon monoxide. And this is going to be carbon dioxide, okay? So this is a situation where we let the prefixes determine the numbers, okay? Because there is no oxidation states that have to add up equal to 0. So these can combine in different ratios. So if you think this through, okay, there's kind of all these rules. But if you think them through and start with this, the simple idea that says, okay, start with this. Am I going to form an ionic bond? Are the elements, it's a binary compound, so if you have a metal and a nonmetal, you know it's going to be on an ionic bond. Do not use prefixes. The only time you're going to use prefixes is when you have two elements that are up here in that far right corner of the periodic table. Start with that idea, because the only time that's going to happen is when you're going to have two nonmetals. They don't have enough electronegativity difference to pull the electrons from each other, and so we have to use prefixes. So start with this first one. Metal, yes, boom. I'm not going to use prefixes. Two nonmetals, hey, I've got to use prefixes. So start with that idea. Okay, so I want to make sure everybody's cool on some of these. So when you get to on page 14, okay? So let's just kind of go through some of these. We started with these yesterday, okay? So you've got, like, for example, you've got one down there, you have bromine pentachloride. Okay? How do I know that there's only one bromine? There's no mono in front of it. How do I know there's one bromine? Addie.
I don't know, because I don't know, I just know.
How do you just know? Grace.
Because there's no prefix.
Yeah, if there's no prefix, guess what? It's just one. Okay? If there was anything else, we'd put di, tri, hepta, whatever. Okay? Okay? So if there's nothing there, there you go. Now, let me give you all a hint. Okay? Literally, if I was preparing for this test, I would get some examples that you know, that you can use as a pattern. Okay? Oh, carbon monoxide, poisonous gas. You don't want to inhale it. Oh, I know that's CO. Carbon dioxide. Oh, that's CO2. If you can figure out the pattern, then it's just replicating this. Okay? That's it. So here I got bromine. Oh, I look at this, go, oh, there was no prefix in front of that carbon when I named it, and there was only one of them. Oh, there's no prefix in front of the bromine. That's just going to be Br. Because if there's nothing else, the default answer is there's only one of them. Now you have to know penta. Anybody ever been to the Pentagon in Washington, D.C.? Okay, how many sides does it have? 5. Okay, so penta means 5. So you're going to have, now what I'm going to do is wrong. Okay, do not do what I'm about to do. Do not do what I'm about to do. Okay, oh, penta, that means 5. So I'm going to have 5 Cl. Horrible, train wreck, bad. Okay, you only use subscripts. Oh, I'm going to take that 5 and I'm going to move that. I'm going to have Br5Cl. Also a train wreck. Why?
Does the CL should have 5?
Yeah, because There's no oxidation states to add up to equal to 0. Penta just means 5. So this is just going to be BrCl5. That's it. Okay? Just look at the prefixes, and that's going to tell you the number. There's nothing weird to it. Okay? That's it. So you got like dicarbon. Sounds like a horrible disease. Heptoxide. You have carbon heptoxide, dicarbon, and you take like antibiotics, or how do you treat that? Okay, so I got dicarbon. Di means how many? Two. So this is going to be C2. Hepta means what? 7. So it's going to be C2O7. So these look daunting, okay? Now, technically, let's say I ask you to name this. If I ask you to name that using prefixes, how would you name it? Dihydrogen. Dihydrogen, then what? Monoxide. So it was this kid. This is many years ago. This kid was it was like a science fair, and he was like a ninth grader. So I think he was out in Utah. And so if you look at the properties of water, okay, number one, it kills a certain number of people in the United States caused by drowning. Okay, it's a solvent. Okay, if you consume too much of it, it's poisonous. Okay, you can actually die from drinking too much water. Okay. And so this kid went out to the mall, and he listed all of these horrible sounding properties of water, okay? But he didn't call it water, he called it dihydrogen monoxide. So he went out and he says, hey, here's this chemical, it's called dihydrogen monoxide, it kills so many people a year, it's a solvent, okay, you know, all of this stuff. And I'd like to have a petition to have it banned. And all of these people signed this petition to have dihydrogen monoxide banned because it sounded scientific, okay? And he listed all these properties. And basically everybody saw that, signed this petition to ban water. So this is why you study science, because you can go, it's water. Yeah, it does have some bad effects on it, but all in all, I think it's kind of important for our existence, so let's not ban it. So it's like, what's the alternative? So, anyway. So, naming those are fairly simple. There's not going to be a lot of that on the test, okay? I'm not going to throw anything weird on it, okay? But I might throw something like this, you know, C2Cl4. So if I gave you that, and ask you to name it. Carter, what would you say?
Carbon.
What'd you say?
Carbon.
No.
No.
There's 2.
Huh? Dicarbon.
Dicarbon.
Oh, I see that now. Tetrachloride.
Tetrachloride. Got it? Cool? Okay, beautiful. All right, now, let's go over to 15. And naming acids. I'm not going to spend a whole lot of time on this, mainly because I spend a huge amount of time in AP chemistry. So all I want you to do is kind of have the basic idea of how we name acids, okay? Now, I'm going to tell you right now, here are the big 3 that we use most often in any lab. HCl, y'all have dealt with that. Anybody remember the name of this?
Hydrochloric acid.
Hydrochloric acid, okay? Hydrochloric acid, okay? Then we have H2SO4. Well, what's the name of sulfate anion? Or SO4 is sulfate, right? So this is sulfuric acid. And then we have HNO3, which is nitric acid. Okay? So those are the three that we use 90% of the time in lab. Okay? We sometimes deal with obscure ones like acetic acid. Acetic acid is basically vinegar. Okay? So acetic acid is HC2H3O. So that's acetic acid. So these are the four. If you go through the entire chemistry program at Hayes High School, those are the four basically that we use. Okay, those are hydrochloric, sulfuric, nitric, and acetic acid. Okay, even in AP chemistry, sometimes we'll use something we would call oxalic acid, but it's really obscure. Okay, and we really don't even use it that much. So those are going to be the big ones that you will use most often. Now, so let's kind of look at this pattern here. So what you have listed here are the ones that have hydrogen as the cation, and then you have various anions. But the same rule applies. So if you look at hydrochloric acid, hydrochloric acid, hydrogen is +1, fluorine is 1-, that's why it's just HCl. Okay? You look at sulfuric acid, H2S. Now, here's one that gets confused a lot. H2S is sulfuric, if I could spell, then that would write, sulfuric acid. H2SO4 is sulfuric acid. And technically that's hydrosulfuric acid. And H2SO4 is just sulfuric acid. So if you look at this pattern, if you see the word hydro in front of it, okay, that means that it's going to be one single hydrogen or two with sulfuric, but everything still has to add up to equal to 0. So when you see the hydro in front of it, okay, and this is just a matter of figuring out the code. So if you look at this pattern, anything that starts with hydro means that it's going to be a binary acid, okay? So again, figure out the pattern on a couple of them. Oh, hydrochloric acid, okay, HCl, boom, there you go. There's a binary compound, and we start with hydro, and here's what's different. Oh, go away. And this gets confused a lot. So this is hydrochloric acid, okay? Now here's what's different. Even though this is a binary compound, this is kind of the obscure rule. We don't change that ending to IDE, okay? It isn't hydrogen chloride, okay? Because it's an acid, that's why we change that ending to hydrochloric, okay? So here's an easy way to remember this. This ends in ic. Acid has the letter CI in it, okay? So if you see HCl, oh, that's hydrochloric acid. I got an ic on the end, I got a CI in the acid, okay? So that's an easy way to remember that. So all of these, listen to the terminology. If it is a binary, meaning 2, acid, the first element is always hydrogen. The second element is always going to be the anion, oxygen or chlorine, fluorine, bromine, something like that, okay? So when you look at these rules, okay, why does hydrosulfuric acid contain 2 hydrogens? Oh, because sulfur has an oxidation state of 2-, therefore you have to have 2 hydrogens, okay? That's one of the very rare ones, and you never really work with hydrosulfuric acid because it's pretty rare. Without doubt, the only one out of all of those, of these binary compounds, like I said, I promise you, on the test, the only one I'm going to ask you about is hydrochloric acid, okay? maybe hydrobromic, that's the other one that's kind of used a lot. But just know if it starts with hydro and it ends in ic, it's a binary acid, and it's just gonna have that anion. Okay, now, where it gets a little bit weird is over here on page 16, okay? So, these are these different acids, okay? And to do these, you really have to have the list of all these polyatomic ions. This is why I'm not going to spend a lot of time on this. I'm just kind of going to introduce you to the pattern here. So if you look on this first one, like in all the labs I've done, I've never worked with chloric acid in my entire life, okay? I've never had. I've never done a single lab with chloric acid because it's so good. But here's the pattern. You have HCOO3. Now right away, this is not a binary acid because I have more than two elements that are here, okay? So right away, I know this is not going to be like hydrochloric because of the fact that it's not a binary acid. So start with that. Oh, it's not a binary acid, not going to end it. So, but the same rules apply. The cation is still H+. Now, when you look at that ClO3, so if you look on either the chart of the common polyatomic ions that I gave you, or on the periodic table, ClO3 is chlorate. Okay? So when you look at how this is named, and this is why I don't spend a lot of time on this, because it's so weird. So your chlorate, okay, that's the name of the anion. But notice when we name it, we change that ending to ic, okay? So this is the cation is the hydrogen, which is always going to happen. The anion is ClO3, but instead of naming it chlorate, we change the ending to ic. So that's what's common with binary compounds. So 8 becomes X, okay? Just remember, 8 becomes X. Now, when you get to sulfurous acid, this next one down, you have H2SO3, okay? So, again, the same thing is going to apply. This has a charge of 2-. That's why I have to have 2 hydrogens, because everything still has to add up to equal to 0. So that's cool, right? My cation is still hydrogen. Now, my anion is SO3 2-. So if you were to actually name that ion itself is sulfite, okay? So if you look at how this is named, again, we're going to change that ending to sulfurous. So ites becomes us, okay? Now, here's the difference. And this is why these rules are so weird, and this is why I'm not going to spend a lot of time testing you on them, because quite frankly, I don't even have them all memorized. I have to sit there in the lab going, okay, us becomes nice. Okay, it's just, this is why God made Google, okay? True story. It's like, you just ask your phone, it's like, hey, what's the formula for this, okay? This is why I'm not going to hammer this on the test. This is just so you have a general idea. So now, if you look at H2SO4, so this is sulfuric acid. So this is sulfate. So H becomes X again, okay? So this is why this is so kind of random in terms of the rules. Literally, we could have, well, if you take AP chemistry, we spend an entire, like 4 weeks just on acids and equilibriums, okay? So that's why I said we're not going to hammer this very much, because it's just not all that important. So, but here's the other one that's kind of down there, this carbonic acid, H2CO3. So if you ever drink a lot of pop contains carbonic acid, or CO2, CO2 turns into carbonic acid. This is actually important if you study what's happening in the oceans, okay? So here's a short version of carbonic acid, and this is why it's important for you guys in terms of a bigger idea. So, everybody taught, here's our Earth, and we have this little layer of an atmosphere. And what's happening is that we're increasing the concentration of carbon dioxide. So what happens is the oceans are actually acting as a huge sink for carbon dioxide, okay? Carbon dioxide is actually being absorbed by the tons into our oceans. And everybody goes, oh, that's cool, but here's the problem. And again, this is a whole long lecture. This is just this is a 2-minute lecture that usually takes 45 minutes to get through. So what happens is that carbon dioxide, and you all are exhaling it right now, don't feel bad. We have to exhale carbon dioxide. It's a byproduct of our metabolism. So you all are exhaling carbon dioxide right now, okay? Don't flip out, it's like, oh, I feel bad, I'm adding to climate change. That's okay, all right? The alternative is you don't breathe, and that's even worse, okay? Just don't waste, use your breath, use it wisely, help the world, okay? So what's happening in the oceans is that this is absorbing carbon dioxide. And when it forms, and it absorbs that, it tends to form carbonic acid, okay? So it doesn't exist as carbon dioxide, it exists as carbonic acid. Well, here's what's happening, is that carbonic acid is known as a weak acid, which means it doesn't separate very easily. So how it exists in the water is HCO3 1-. So what's happening is that clams need to build their shells, okay? To build their shells, they need calcium, okay? That's what they do, they need calcium. So they take dissolved calcium in the water, and they form calcium carbonate, otherwise known as limestone. So if you've ever seen limestone, okay, if you go to K-State, KU, any of the major universities around the state, the buildings are made out of limestone, it's calcium carbonate. If you drive up to Kansas City, you drive through the Flint Hills are calcium carbonate. If you've ever seen concrete, concrete is pulverized limestone, which is calcium carbonate. So calcium carbonate is one of the most important things that we have in terms of a building material. Okay? And by the way, it's not soluble. It doesn't dissolve in water. If it did, we wouldn't build buildings out of it. Oh, look, we built this great building out of limestone, which is cool until it rains and then it dissolves. This is why we don't build things out of salt, because salt is soluble. It's like, oh, let's build a house out of salt. Great if you live in a desert. Sucks if you live where it rains. It's like, what happened to the house, honey? I don't know. I came home and it was gone. It just dissolved. Sorry. I should have paid attention to Brookham's chemistry class. My bad. So you have all these buildings that are made out of calcium carbonate. Well, all of that calcium carbonate was formed millions of years ago when Kansas was covered with an ocean. And you had all these clams that had built their shells out of calcium carbonate. They settled to the bottom, years and years of compression, all this good stuff, we end up with limestone, okay? So this is what limestone is made out of calcium carbonate. So what's happening is that we're finding these oysters and things like that. What's happening is that there's not enough carbonate to form calcium. So they have the calcium, but they don't have enough carbonate because of the fact that that carbonate is being tied up as carbonic acid. So we've shifted this equilibrium. So what they're finding is that young clams especially, their shells are very, very thin. They're not thick like they should be because they have enough calcium, but they don't have enough carbonate. So the shells are becoming very thin. So what they're seeing is a collapse at the bottom of the food chain. So these young clams, which should develop into older clams and reproduce and things like that, because they have such soft shells, aren't living long enough. So what the fear is that you're going to collapse the bottom of the food chain. Well, guess what happens when you collapse the bottom of the food chain? Everything else above that, the salmon feeds the orcas, up it goes. So if you collapse the bottom of the food chain, you're going to collapse everything else up on top of it. So that's going to be the fear. Okay, so I want to go through page 17. So here's what I want you to do right now. I'm going to stop talking for about 5 minutes. There's this chart on 17, and it combines everything. There's ionic compounds, there are covalent compounds, there are acids, the whole smash. So I'm going to stop talking for 5 minutes. I'm going to shut off that camera. And we're going to go over this, but I want you to treat this as the test. The only thing you're going to have available to you is a periodic table. Okay? So what I want you to do, we're going to go over this to make sure everybody has these right. Okay? So I want you to treat this as the test. You have your, not that one, but your other periodic table, the one that doesn't have the chart on the top of it, okay, the more colorful one. That's what you're going to have on the test. So what I want you to do right now is I want you to go through and I want you to try and work every one of these, because if you can do this, you can pretty much do the test, okay? If you can't, this is going to show you where your weakness is. So right now, try and do that. Stop that camera. The N2O4.
Covalent.
That's the only one that's covalent, okay? It's the only one that has the two nonmetals. So this is the only one that is, oh, start that back up again.
I did.
Oh, you did? Okay. So, because it's covalent, you have to worry about the cation and the anion. Ramen.
No,
Why?
because it said it's a compound, let's take these boxes.
It's not the bigger picture. Why don't you form cations or anions?
I don't know.
Robin,
Uh-huh.
if you cohabitate with someone, what does that mean? Or if you cooperate with someone, what does that mean?
Work together.
They're working together, okay? So this is a covalent bonds, right? So what are they doing with the electrons? Are they transferring them or are they sharing them?
They're sharing them.
Because they're sharing them, you don't form ions. And because you don't form ions, you don't have to worry about the oxidation states adding up to equal to 0. Okay? Because they're just sharing their electrons. It's a hippie thing, right? So, Izzy, how did you name N2O4?
N2O4. How did I name it?
Yes.
Okay. Well, because it's nitrogen,
Yeah.
and because there's the O and it's 4,
Yeah.
then I put 8 at the end. So nitrate.
Okay. Here's the deal. It's a binary molecular compound, right?
Uh-huh.
So start with the 2. How are you going to indicate that there's 2 nitrogens?
Di.
So you got dinitrogen.
I'm still doing that.
So you got dinitrogen, right? Now, we have 4. What's the prefix that indicates 4? So, tetroxide. Okay? Boom, there you go. Okay, there's no oxidation states because nitrogen and oxygen combine in different ratios. Now, then you have FeCl2, right? Ionic compound. Iron, metal, non-metal. Big difference in electronegativity. We're going to form ions. So, this is an ionic bond. Fe is Fe2 plus is your cation, fluorine is your anion. Now, what's wrong if you just put iron fluoride?
You need to indicate
You
that
have
it's
to put
2,
You have to put the Roman numeral 2. Why?
because there's more than one oxidation state.
More than one possible oxidation state. If you take this 2 and you move that up, this becomes iron 2 chloride. Okay? Now, the next one down, you have hydrochloric acid. Hydrochloric acid, I promise you, if you hand in the test tomorrow and you have not written or named hydrochloric acid, you have done something wrong. Okay? So you have hydrochloric acid. Formula for hydrochloric acid is what, Ethan?
HCl.
HCl. Hydrogen is my cation, fluorine is my anion. It's an acid. There you go. Bless you.
Thank you.
Now, follow this pattern. Okay, that was hydrochloric acid. So HBr then is going to be hydrobromic
Bromine?
acid. Okay? Now, you have manganese 3 oxide. Peyton, what does that Roman numeral 3 tell me?
It tells you that the manganese has an oxidation state of +3.
Fantastic. So I've got Mn 3 plus. What's the oxidation state of oxygen? You have to know this without hesitation. What's the oxidation state of oxygen?
2 minus.
2 minus, because it has 6 valence electrons. Oxygen promise, one of the most common ones, okay? So oxygen has 2 minus. So how am I going to write the formula for manganese 3 oxide? Emma,
MnO3.
Mn03,
Mn2O3.
Mn2O3, okay? Because you're going to swap those oxidation states and make them become the subscripts, okay? Hey, you got to know the terminology. Hey, these are subscripts. Now, here's how you can check this right. How can you check if Mn2O3 is the correct ionic formula? Keaton, what do the oxidation numbers have to add up to? 0. If I can come in here and go, take Peyton's information, says, oh, I think manganese is 3 plus. 2 times 3 gets me +6. I got 3 oxygens. That's -6. Guess what? They all add up to 0. That's how I got it right. Now, Emma, here's how you go to check if you had put Mn03, you would have known that was wrong. Because if you had written MnO3, oh, I got 3 oxygens, that's -6. Manganese is just 3 plus. If I take 3 plus and add that to -6, I get -3. That's a train wreck. It doesn't add up to equal to 0. So that's why if you go through that extra step, you can always check that you have your ionic compounds right, because you can check, oh, do they add up to equal to 0? If they don't, hey, at least I got a fighting shot. If those oxidations don't add up to equal to 0, you know it's a train wreck, okay? You know it's an absolute train wreck. All right, now, the MNO, that's a little tricky, okay? Because here's what you're tempted to do. Promise you, this is where this goes south most of the time. One of 2 things is going to happen when you have that MNO, okay? You're just going to name it just straight up manganese oxide, okay? What's wrong with that? Miles, what's wrong with that?
It needs a 2 at the end of manganese.
Yeah, because manganese is like the poster child for multiple oxidation states. Okay, it is the absolute poster child for multiple oxidation states. Now, here's what you're going to do wrong. You're going to look at that and go, oh, there's 1 manganese. I'll call that manganese 1 oxide. Okay, that's the other thing that you're going to do wrong. Now, why is that wrong? Luke, why is it not manganese 1 oxide? I have 1 manganese.
Because you don't have, it's implied, you don't have to put the Roman numeral, isn't it?
This is why science teachers have flat foreheads.
Is it because oxygen's oxidation state is 2 minus?
Yes. Start with your anion. What's the oxidation state of oxygen? Always 2 minus. There is no exceptions except for hydrogen peroxide, and don't worry about that. So, Luke, if oxygen is 2 minus and everything has to add up to equal to 0, what does the manganese have to be?
2 plus.
2 plus. So therefore, we get manganese 2 oxide. Now, here's how you can check this right. Make the door swing the other way. Okay? Literally, make the door swing the other way. Let's say that you had written incorrectly. Let's say you had written manganese 1 oxide. And you say, hey, I'm going to try and write the formula. And all I know is that it's manganese 1 oxide. Well, if you try and do that, you go, oh, that's Mn1 plus, oxygen is 2 minus. Boom, that becomes Mn2O. I don't end up back with where I started. So that's why manganese 1 oxide is wrong. Manganese 2 oxide works, okay? And if, let's say, you just put manganese oxide, little bells and whistles should go off and go, oh man, manganese, I have to have more than 1 oxidation state, okay? Since you have to have more than 1 oxidation state, that's why you have to have those Roman numerals in there. Okay. NH4Cl. Now, what I'm going to do is wrong. Okay? Do not do what I'm about to do. Here's what some of you are going to do. Trust me on this one. You're going to look at that and go, oh, these are nonmetals. I have to use prefixes. And you're going to try and go, you're going to make this horribly complicated. You can go, oh, that's nitrogen. I've got four hydrogens. That's like tetrahydrogen. And then I got one chlorine, and that's monochloride. Okay? That's what you can try and do. Trust me, seen it? Wrong. Okay? First off, is it a binary molecular compound? No, it's a tertiary compound. Okay? We got all sorts of things going on. So, right away, that's bad. Stop. Don't. Okay? Stop. What's NH4?
Ammonia.
Ammonium. So this is just going to be ammonium chloride. There you go. Got it? Those are your pitfalls. Okay. Okay. So, this is your last big culminating assignment, okay? If you, and yes, this is due tomorrow, okay? There's a total of 31 formulas. Either on the front, I give you the name, and I ask you to write the formula, and then I've got some questions down here about what's wrong with all of these. And then on the back side, I've given you the names, and I'm expecting to be able to write the formulas. Okay? So, excuse me, I've given you the formula, expect you to be able to write the name. So, now, what I would do if I were you all, okay, this is what I would do if I were you all. I treat this like the test, just like you did. I'd sit there and go, I have that colorful laminated periodic table. That's all you're going to have on the test. So I would go through here and I would try and figure out the ones just using that periodic table. Now, there are some of these that are weird in terms of like the chromates. So I've got like strontium chromate. Chromate isn't one of those that I expect you to have memorized. Okay, so some of those polyatomic ions, if you're sketchy on those, and it's like, oh, okay. If I expect you to, like on the test tomorrow, if I gave you chromate, I would give you the formula for chromate. Okay, but like for example, this first one is magnesium sulfate. You have to know sulfate, boom, SO4 2 minus. Okay, you have to know that. Oh, magnesium is 2 plus. Oh, magnesium is 2 plus, sulfate is 2 minus. It's just MgSO4. So this is a combination of ionic compounds. There are molecular compounds mixed in, okay? Binary molecular compounds thrown in there. There's ones where you have to put the oxidation state. There's some where the Roman numerals to indicate the oxidation state. There's other ones that you don't, okay? So this is, if you can do this, and you can feel good about life, you're probably ready for the test. If you go through this and you go, man, it's tough, okay? You have to figure this out. Now, on your Google Classroom, I sent you that electronic version of this packet. There are videos on there that explain all this. There is the game, okay, that we talked about, that app that you can download. This has to become automatic, okay? And there's no shortcut to it. Like, it just takes practice. Now, if you want to visualize with these ionic compounds, little pieces that you cut out and it fits together like lock and key, and you like that, that's cool. Okay, do that. If you like doing the electron dot and that works, that speaks to you because you're a visual type person, go with that. If you just like, oh, I'm going to swap out the oxidation states, and make everything add up to equal to 0. If you're more of a math person, so there are like 3 different ways that you can think this through. You have to pick the one that is most comfortable for your learning style, okay? That's what you have to figure out, but you have to figure that out. So tomorrow, we got one short lab that we'll do, deals with percent compositions, and then we're going to basically spend the rest of the day reviewing tomorrow, test on Thursday, okay? Got it? Good. Now, don't worry, there's this whole big section on Lewis dot. We've actually already done that, okay? So we'll spend a little bit of time talking about a little bit of stuff on that Lewis dot, but don't worry about that. So what I'm going to expect you to have done is through page 17, okay? That's what I'm going to grade. We did the Lewis dot on another assignment, so don't worry about that part of it. If you want to read through it, there are some things I do want to touch on tomorrow, but we'll kind of go over that. So what I'm going to expect you to have done is through page 17.
Do we have
Okay.
to do page 4?
No, we'll talk about that. So basically what I'm going to expect you to know is from page, where was that at? 7 through 17.
So that's all we need to have done, so.
Yep, 7 through 17. That's it. Okay, I'm gonna hand this out. What I would do is I would treat this as the test. I would go through and I would work it, the ones that you don't know, go back and look at. And if you have any questions on these, like tomorrow, because I want you all to be successful, obviously, on this test. So if you get done and you're not sure if you're right or wrong, ask me. I will tell you, okay? Because this is something, you have to have this right. All right, so stop that. I'll hand this out.